Let's go. Ok. Bonjour à tous. Merci aux courageux qui se sont connectés aujourd'hui pour suivre le séminaire du jour. Donc aujourd'hui, on a la chance de recevoir professeur Thomas NIENDORF de l'université de Kassel en Allemagne. So now I'll switch to English. Thank you very much, Thomas, for being here, for accepting to take part in this seminar series. You will have about 45 minutes or so to present your work, and then we will have a few questions for you. I will take care of anyone trying to come into the virtual room and stuff like that, so you don't have to worry about it. You can just focus on your talk. And I'd like to thank you again, and whenever you're ready, you have the floor.
Okay, Justin, thanks a lot for the kind introduction. It's my pleasure to be here today to present some of our recent results on 3D and 4D printing. So the main topic is, as you can see, direct microstructure design, and this is one of the things we do in a lot of different materials, and thus this will be the focus of my talk today. So just to have a look on the map of Germany at that point. So where is Kassel? Kassel is not known to everyone, I guess, because it's not a really big city, 200,000 people living there. And you can see it here, it's in the heart of Germany. So in between Hanover and Frankfurt, from Frankfurt, it's about 1.5 hours by train. So very convenient to get there and to get to any place in the world thereafter. So Kassel is well known for a lot of things. It's a green city, it's World Heritage Site, really nice parks, and it's well known for Documenta. So for an arts exhibition that takes place every 5 years, and the next Documenta will be next year, hopefully. We will see, but they are all optimistic that we will have a normal kind of Documenta in 2022. You can see the building where I'm sitting in on the upper right here. So this is mechanical engineering, materials engineering department being here, focusing not only on metals. So this, of course, is my field of research. There is plastic science as well. So the major groups of materials are being focused in our research. So this is the major research topics in my group. So we are concentrating on process microstructure property damage relationships in a lot of different materials, so from structural alloys to shape memory alloys. And to do so, we look at residual stresses, we look at, of course, additive manufacturing, on shape memory technology, and on surface engineering and fatigue. So this is the main columns of our research, just a few snapshots in the next slide. So this is just some more details on this. So looking at the alloys we are looking at, so in principle, a lot of different high strength alloys, majorly steels, then high temperature alloys, nickel-based alloys, for example, and the shape memory alloys I already talked about. A good thing we have is a lot of systems for in situ characterization using digital image correlation and other techniques to really have an in-depth insight into the local mechanisms that take place at a given loading scenario. And just as I said, a few snapshots from the lab. So this is just some welded steels where we look, of course, into the weld zones. This is own built diffractometer for X-ray stress analysis, hole drilling technique as another technique to determine the residual stresses, some processes that are in focus of industry, so band straightening, again, the role of these kind of processes on residual stresses, and then afterwards the role of residual stresses on the overall fatigue properties. So this is deep rolled steels, metastable steels, where we can have deep rolling even at cryogenic temperatures to induce some martensite in the upper surface to have really superior residual stresses to really promote a superior fatigue response. In terms of shape memory alloys, just as few examples on the left-hand side, and this is focusing on iron-based shape memory alloys. So we are really active in this field. So iron-based are kind of cheap shape memory alloys that can be used in civil engineering applications. And for these purposes, there need to be some new developments in the field. And we are active in 2 of those iron-based shape memory alloys that show really good subelastic response. And so they are really promising for such kind of applications. To do so, again, we have, of course, to analyze the microstructure to a certain depth. In this case here, it's Newton diffraction we are looking at to look at order parameters in those alloys. And this is not iron-based. This is cobalt, nickel, gallium. We will see later in my talk our recent work on additive manufacturing of cobalt, nickel, gallium. So cobalt, nickel, gallium as a promising high temperature shape memory alloy as well here in the upper part, just to have some snapshots of in situ characterization. This is a compression test on a polycrystalline sample, and we can see that there's a lot of things going on at the surface when we compress the sample, and this then is linked to the response and to failure thereafter. So we see a crack forming at the grain boundaries, and by this we are able to distinguish between good and bad grain boundaries, and this is one of the aspects that is resolved by in situ characterization. The lower right, this is abnormal grain growth stimulated by cyclic heat treatment, again an iron-based shape memory alloy, where we need to get rid of these triple points, and this can be done by grain growth with a really, really simple approach, just using some specialized type of heat treatment. So now coming to the field of additive manufacturing, this is our national partners, some of them. So some partners from Paderborn University, where I did my master thesis studies. Then I went to Freiberg, close to Dresden. So again, a lot of collaboration there in that field. Companies, SLM Solutions as a machine manufacturer, Föst Alpine as a powder supplier, and some other institutes we are working with in the field of additive manufacturing. And this is only the national partners. Of course, there's a lot of international partners as well. So just to have the names here on the slide, I just would like to define, as this is not really scientific, when I use the word 3D printing, I'm focusing on additive manufacturing of structural materials. So the classical type of additive manufacturing, we will see of some of the machines we use for that. And when I talk about 4D printing, in my case, this is of course additive manufacturing, but of materials there that can change the shape up and providing any kind of stimulus that could be, for example, temperature. And so in my case here, you will see that later on, 4D printing is 3D printing of shape memory alloys. So just a look into some literature of last year. So this is a well-known Gartner hype cycle, and this is from 2015, as you can see. And there we had the enterprise 3D printing. So the professional 3D printing already almost at the plateau of productivity, so being fully mature at that point. And in 2018, we see 3D printing is not shown anymore here on the curve, but there's another thing coming up, and this is here the 4D printing. So this is just growing in expectations at that point. So a new field coming up in 2018. So this went up for some of the positions right now, and so this is one of the hot topics, and quite a lot of people are working on this, but it's even more challenging than 3D printing of structural materials, as you will see later on. So this is additive manufacturing, of course, a very broad field. I will be only focusing here on the right side today, metals, using powders and using 3 different kinds of techniques. Laser beam melting in powder bed, electron beam melting in powder bed, and directed energy deposition, so sprayed powder to have another technique to do rapid screening of alloys. Just one example why additive manufacturing, I think everyone here knows there is of course a lot of advantages. The speed of processing is not the advantage. So to have a huge part in place takes quite some time. And if you try to just copy a component that can be manufactured anyhow by standard techniques, there's no reason to do additive manufacturing. We have to find the right parts. And this is a very simple schematic example, just this ladder structure embedded in a hull. And of course, this is for complexity. And complexity has to be a key in finding the right parts to be printed, to be additively manufactured. So this is what I tell my students. So look at those parts and really think about, is this better to be printed or manufactured traditionally? And if it's complex, or if you can replace a group of parts by just one part, if you use additive, then that's a reason to really think on additive. But don't try to print any kind of needle, whatever. So this is done in traditional ways much more better at that point. Looking at additive manufacturing and looking not on the shape, but looking at the materials. Even if we use standard materials, we will gain new materials as the processing is done in a different way, and as those processes are characterized by really unique features at that point. So we have rapid solidification, we have intrinsic heat treatment, and this forms, even if considering old-fashioned materials, this forms new microstructures, and theirs can lead to really excellent properties, even if not expected. I will show some of those results later on. And in this case as well as in terms of geometry, there's almost no limits. So we have to think additive in terms, of course, as seen before, geometry, but also in terms of microstructure and materials properties. For that, we need to understand, however, the correlation of processing conditions, microstructure evolution, the properties arising from those microstructures, and the damage evolution in those cases. And this has to be done to really be able to put those things in use. If we are not aware of those correlations, we will not be able to use those materials. And as I said, there will be some examples today focusing on the three different approaches. So I think everyone knows here in the audience how to print a part. First, we have to have a model in CAD. Then we slice this model into layers. This information is transferred to the machine. In this case, selective laser melting. We do the coating. We have the powder bed, we do the coating, then we expose by laser irradiation given spots of the powder bed to melt the powder there. And if this is done in the whole layer, we can lower the platform and the thing starts again to have the circle. And if this is run a lot of times, we will have our parts to take them from the powder bed and to put them maybe directly in use. Not in many cases, I guess, because we will have rough surfaces and so on, and we need to think about surface conditioning at that point. This is the two machines I have in my labs, an SLM Solutions 280 equipped with two different laser sources and a platform that can be heated up to even 800 degrees C, and an Arcam EBM machine. So again, a powder, but melting is done with the electron beam, and we have process temperatures up to more than 1000 degrees C. So a hot bed process. Normally SLM is run up to 200 degrees C as a maximum for platform temperature. So this is already a very specialized platform we are using. And this is the agenda of my today's talk. We will look at those two topics, 3D printing and 4D printing, and I will guide you through the slides in the following. So current challenges, the work of more than 5 years summarized in 2 slides. So this is a summary of the work we did, focusing on structural materials. So materials for additive manufacturing have to address the following challenges. They have to be damage tolerant. Many of those are not. then we have to get rid, in many cases, of the factor of anisotropy. We have to get rid of the factor of residual stresses, and we have really rapid precipitation that can be good or detrimental, depends on the field of application at that point. And that's just shown by a few examples. We will see a lot of those examples in the following in my talk, so I will not go into detail at this part here. We will see this later on. So just very, very shortly, briefly, process microstructure property relationships in Ti-6-4. So of course, Ti-6-4 is well known and many times used in additive manufacturing. So this was built by selective laser melting, and the initial microstructure evolving from the process is this as-built microstructure being martensitic in nature, being very brittle at that point, and this can not be really used directly in application. So any kind of post-treatments have to be done, either only heat treatments as in 2 and 4, or hot isostatic pressing, a well-known process as well. So heat treatment with a superimposed pressure to get rid of the pores. And this is, of course, one very important aspect. But it's not only the pores at that point, it's as well the residual stresses. And this is just one example, plus 775. This is tensile residual stresses in Ti-6-4 processed at 200 degrees C. So really detrimental for any kind of application. So we have extremely high residual stresses, and those high stresses are not directly at the surface, they are below the surface somehow, as is shown here for, in this case, 316L stainless steel. So we have to look at distinct points to really get to know what is the absolute value we encountered after processing. But I will show that this is not that simple to really do a critical assessment of residual stresses, at least in structural complex components. So this is Ti-6-4 and fatigue, so Wöhler type SN curves in this case here, and we see two groups. A lot of lines, colorful here at the bottom of the plot, and there's the green point in the line. This is the condition hot isostatically pressed at 920 degrees C. So in our case, the optimum parameter, there may be even better parameters at slightly lower temperatures, but anyhow, this is quite good. So this is as good as conventionally processed Ti-6-4. What the reason for this? If we do additive, we always will have some porosity in our parts. So this is a computed tomography scan shown on the left-hand side, and we see some pores. Resolution here of the system we used at that point, 22 microns. We have now a system in place being able to resolve pores down to less than 1 micron, so a resolution in the nanometer range. So still there's pores in there, but they are under critical in size. And with the 22 micron resolution, we see almost this condition being pore-free. But of course, it's not pore-free, but they are not critical anymore, the remaining pores. If we look at fracture surfaces, and we did a lot of fracture analysis in these studies, we see in the non-hip condition, the cracks, and this is now in very high cycle fatigue regime, the cracks always evolve in direct vicinity of defects. And this is a classical lack of fusion defect where the crack starts and then grows and finally leads to failure. If we do the same analysis after hip, we see there's, of course, fracture. We do fracture on any kind of material. You just need to decrease, of course, either number of cycles or the load. And then we will see a crack or a fracture surface. And here in the fish eye, we see there's no pore starting the crack. Here it is just a lamellae of the Ti-6-4, so an alpha lamellae, and this is inclined by about 45 degrees, and this is the most critical feature in that point. And so the remaining pores less than 10 microns in diameter are not critical anymore, and this is the evidence that this statement is correct at that point. Anyhow, this was all done on very simple specimens, so cylindrical specimens tested in the lab. We did some tests on real components as well. This is a bracket that could be used in aerospace industries, of course, this is not a real part, then I would not be allowed to show this. It's a simplistic model of a bracket. So we had some loading scenarios that were derived from aerospace applications, and we did some topology optimization at that point, and this was the structure that was calculated, that was built thereafter. And looking at this part with high degree of complexity, we can see that not all parts are built upright. So not all the parts are built in Z direction. So we have a lot of inclination angles of the surfaces towards the platform. And just looking at one single aspect here, this is the residual stresses again. We did a lot of residual stress measurements on differently inclined surfaces. And the value you obtain is dependent on the angle of inclination. So there's no real spot to really measure a characteristic value for residual stresses. So this is dependent on the inclination angle between the platform and the surface of the part. And so it's really tough to provide one single value that shows the characteristic residual stress state of a component. And not many people have this in mind. Unfortunately not. So that is all I can tell about TIE 6.4. I now would like to go to the field of direct microstructure design. And for this, we use the 280 system we have in the lab, and we use those two different laser sources we have. The 400 watt laser and the 1 kilowatt laser both have a different profile. We have a Gaussian beam profile on the left here for the 400 watt and a top head profile for the 1 kilowatt laser. And this has a huge effect on solidification of the material, as will be shown on the next slide. This is a component built from 316L, and we have one component. This is one build, only process different parts with the different lasers. And you see here the fine-grained microstructure. Below, we have a columnar-grained, coarse-grained microstructure built in one build, as I said before. So what the reasons for these differences? It's known. It's the thermal gradient and the velocity of the solidification front. And by just manipulating this, we can have the crossing of the line between those two regions. And so based on adequate process design, we can have within one build equiax microstructures and columnar grained microstructures. So in this case, this is done for purpose. So by using different lasers, different scanning strategies, but this can be somehow expected when thermal history changes. And thermal history changes when we change the dimensions of the part. So if we build filigree structures, as is shown here for such kind of lattice structures, we use the same kind of parameters we always use for 316L, but shown below here, depending on the diameter of the part, we can have a change in solidification conditions. And this has to be attributed to, of course, the whole thermal setup in the machine. And this is affected by geometry at that point. And you can see here the fine-grained microstructure on the right. This is a cylinder with a diameter of 5 millimeter. If we go down to 0.65 millimeter, we have the elongated shape. So just by change of geometry, we change the microstructure in the part. And this is in many cases not considered if people do modeling. They do complex structures. They just do modeling on those structures, and they imply in every part the same kind of material with its characteristic values, and this is not correct, at least if we come to such kind of filigree structures. Because then we have to consider an isotropy. We can see some inverse pole figures here on the right, and in case B here we see a very high texture intensity in 001, really in line with the red we see here in the EBSD plot. This is colored for Z direction and so build direction. So this has to be considered at that point. Doing so and using this as an advantage, we can directly build microstructurally graded samples. And this is shown here on the right. This is a block of 316L. This is mostly fine-grained material, but we embedded islands built with the 1 kilowatt laser. And there we got the coarse-grained microstructure, and doing a tensile test afterwards, after cutting a sample from the part here, of course, where the material is coarse-grained, the strength is not as high as in the surrounding layers, and thus doing a tensile test will lead to deformation mainly in those coarse-grained parts. So we can tailor locally the properties of the material by using those process windows we found before. And doing so does not only affect mechanical properties, as I showed before, we do affect other properties as well, magnetic, electric properties. So this is just an example where we used eddy current technique to find out about the local microstructure. So this is the readout of the local microstructure non-destructively by eddy current. And by this, we are able to implement some codes. So this can be then implemented in the microstructure, copy protection codes, whatever. We can write names into components. And this is of course very interesting, as this can be done not only at the surface as we did here, this can be done beneath the surface as well. So we have copy protection markers not being identified by naked eye inspection. This, of course, is a kind of copy protection of the next generation at that point. So up to now, I showed this only for 316L, as this is really, really a nice material to be processed for sure, but that can be done in other alloys as well. We can see here those strongly columnar microstructures, for example, in nickel-based alloys. So this is Inconel 718 in this case, but this can be achieved in other nickel-based alloys as well. And just going to the edge of the things that are possible, we can even build single crystalline materials from this. So this is a single crystal built in Inconel 718. And you can see here the scale bar. This is 5 millimeter. So we can build in the millimeter range single crystals from powders. We just have to adapt the processing windows. So I'm allowed to show this for Inconel 718, but of course this is not the most interesting nickel-based alloy in this regard, but it's possible in other alloys as well, I can tell you. Okay, so this was moving by process parameter design to single crystalline materials. Now we will move into the other direction. So we want to get rid of the factor anisotropy. And on the right-hand side, this is just taken from literature, we see a 316L, so a stainless steel processed by electron beam melting, and we see the columnar grained microstructure we saw before for the 316L I showed we obtained based on selective laser melting. So in this case now, we can see here, we have a different material. So this again is a stainless steel, or an austenitic steel, not stainless steel, it's an austenitic steel. And in this case, we see the microstructure is fundamentally different. So this is a fine-grained microstructure that has been processed by EBM, and this is EBM as-built material. So the question arises, what's the difference between those two steels here at that point? Why do we get such kind of fine-grained microstructure in case of the chromium manganese nickel trip steel? This just to show, if we do heat treatment afterwards, we have the coarse grains again. So this is really a unique structure obtained just by EBM processing. It's possible by SLM as well, but in this case, I only have the EBM material here. There's a challenge. The loss of manganese. Manganese tends to evaporate, especially when doing processing in the EBM machine, where we have a vacuum atmosphere surrounding the build. And in this case, this has to be controlled for sure, as this is really important to have the right mechanism in place afterwards. But based on those process maps, we are able to control this, and we can even have chemically graded microstructures where some parts of the material show a trip effect, others not, and this just by, again, using the right process fences. In this case, the process windows to lead to a controlled evaporation of manganese. Looking at the phase diagram of the material, so this is just some calculations we did with our partners in Freiberg, and we see some differences here in those phase fields as compared, of course, to the 316L. And this is very important at that point. We just built some single layers, single tracks on top of each other, and this was just to avoid any kind of intrinsic heat treatment in the uppermost layer at that point. And looking at this, we see those columnar grains. So solidification takes place in the same manner it did before in the 316L, and only by intrinsic heat treatment, as this is layer by layer processed, we have a refinement during processing induced by intrinsic heat treatment. And this is shown here on the left-hand side. And this is just a schematic drawing, so it's not real temperatures we measured, just for purposes of showing the effect. Of course, when we do the melting, we have the liquid, it solidifies, and then by processing of the next tracks, we always put some heat into the next melt pool, and this has to be somehow transported through the already solidified material, and this is the nature of the intrinsic heat treatment we have in additive manufacturing. And this here now, as is shown on the left-hand side, this promotes multiple phase transformations. And by doing those multiple phase transformations, we refine the microstructure so that we have this fine-grained microstructure after processing. This is grain refinement induced by phase transformations induced by intrinsic heat treatment. So this is all on the structural materials. We will move forward to 4D printing. This will be a somehow shorter chapter at that point. So in principle, all the things we know from 3D printing, the things we did for the last 5 years, we only have to transfer to 4D printing. So this in general is the idea. It's not that straightforward I expected 2 or 3 years ago. But let's have a look. So first of all, many work in that field has been done on nickel titanium. Of course, the world-known shape memory alloy is nickel titanium. So a lot of people did a lot of work on nickel titanium. And this is the worst case material for additive manufacturing. I can tell you from own experiences. So this is really bad. There's some process windows. You can obtain some good material, but those are so small that the choice is not the best, at least in my opinion. So there's a lot of work done, as I said, and there's a review paper from colleagues in the US, Elahinia Group, and 2016, really a great review on all the activities in that field. And looking at this review, of course, there's some work that already has been done in the early years of 2013, and they show those lattice structures, but they only show the geometry. So this has been printed, but it does not really work out. So no one showed up to that point, up to 2016, any promising mechanical results on those lattice structures because they show brittle failure. They don't show any good response at all. And then there's a lot of activities that started in the US, and they were able to print some good parts and to open up some new prospects in that field. And this is just U-shape material they printed, and then they did some heating up to initiate the shape memory response. And as you can see here, one initial response is at 60 and the other at 100 degrees C. So we see responses in different parts. So first the left-hand side forms back to the U-shape, and then afterwards at 100 degrees C, the right-hand side. And so they have a material being equipped with 2 different transformation temperatures. That is, of course, good, but it's hard to control because control of microstructure is the key, of course, in nickel titanium, because this is extremely sensitive to any changes in microstructure and mechanical or chemical composition. And thus, it's hard really to control, as intrinsic heat treatment will lead to different properties in each volume element of the part processed. And this is the reason why there's not so many results on additive manufacturing of nickel titanium based alloys, including nickel titanium hafnium, for example. There's hardly a processing window allowing for robust application of those structures. And so I think it's worth to look at different shape memory alloys. And this we will do right now in the remaining minutes of my talk. So there's a lot of different shape memory alloys in the world. And we looked at iron-based shape memory alloys as shown here in the bottom. What is shown here, transformation temperatures and reversible strains. So we see there's some promising alloys with high strains they can show, and this is one of the options, and the other is the cobalt nickel gallium alloy, where we looked at compression and tension samples. So of course this here is very promising field, high transformation temperatures and high reversible strains. In principle, one of the iron-based alloys we have in focus, very interesting alloy, iron, 34 manganese, 15 aluminum, 7.5 nickel. And this shows a unique phase transformation between an BCC and an FCC phase that allows for reversible transformation. And looking at this, it shows some really unique properties, such as a very low Clausius-Clapeyron relationship, or the slope of the relationship, and thus it's promising for application in civil engineering structures and other structures as well. And in principle, the microstructure is very sensitive to a few aspects. We need to have some secondary precipitates, so-called beta phase nickel aluminum type, and we need to get rid of triple points to have those oligocrystalline microstructures, as shown here on the left, where we avoid those triple points, ductile phase on the grain boundaries to prevent them from cracking. And this can be established by conventional processing, of course, but it is, of course, very interesting to establish this then by additive manufacturing, so by direct microstructure design. And that was the principal idea of that part of the study. Let's try to have a kind of unique microstructure in those alloys. And this is one example where we did first studies showing that we have a quite good pseudoelastic response. So we can see the applied strains up to about 10% cannot be fully accomplished and reversed, but to a large degree. So a good response of the material in compression at that point, because we had a lot of cracking issues. There were a lot of cracks inside the microstructure, hindering any kind of application in tension. So we went to high temperature SLM processing at that point. So some joint work with colleagues from Dresden. And this was processing at 500 degrees C. And you can see those unique elongated microstructures. So the right way to hinder cracking at those grain boundaries. We even did some abnormal grain growth heat treatments to promote an even coarser microstructure. And we can see we are able to come up with a microstructure being hardly affected by critical grain boundary arrangement. This is not the optimum, but it's the right way to come to this aim. And so this is a first response of the system. So this now is in tension. So this is the first curves showing a good response of a shape memory alloy in tension. And this was based on the microstructures I showed before we established in the iron, manganese, aluminum, nickel system. So this is one important step towards an aim. So, and this is what we are still working on, improving the properties of those alloys. We went now to other techniques for processing to even have some more options in alloy design. But this I will not show for the iron system. I will go to cobalt, nickel, gallium to show this right now, and this will be the last chapter of my talk today. So this is single crystalline material, cobalt, nickel, gallium, and you see a good pseudoelastic response of the system up to even 500 degrees C. So this is a high temperature shape memory alloy where we can have really unique properties even at very high temperatures. And so that's the reason why we had a look on the properties of single crystals at the first glance, and then we moved to additive manufacturing. This is selective laser melting. We see a columnar grade microstructure, but a lot of distortion here inside the microstructure, stemming from processing at only 110 degrees C at that point. And this leads to residual stresses and many other factors just hindering a really good response. What we see as well is a lot of cracks. So this is a cobalt nickel gallium sample processed at this temperature, and we see networks of cracks being present in the microstructure. So this is a computed tomography scan of the whole sample. And of course, this will never ever show a good response in tensile testing, for example. So we first had a look if we are still able to get any response in terms of reversible transformation. And this is a DSC at that point, and we see the two peaks here. So it shows in principle shape memory response at that point, but the cracks hindered any kind of mechanical testing. So we move to DED, so the spray and powder process, and this is the microstructure alongside BD. This is columnar grained, and we see it's almost in single crystal. This is only minor misorientations that are showing up in the microstructure, and so this is highly anisotropic, almost single crystalline material processed by additive manufacturing. Looking at the pseudoelastic response at 100 degrees C, we see an answer that is almost as good as in case of a single crystal. So there's some remaining grain boundaries leading to cracking afterwards when we go to this very high strains, but in principle, this really works excellent, and we are able to print those in a large quantity at that point. So there's a solution to the limitations imposed to conventionally processed materials. And this can be even transferred to more complex structures. Doing so, we can have functionally graded structures at that point. And what is a functionally graded structure at that point? I just need to go very rapid through this chapter. As I said before, this is the code we could implement in the steel. This is some unique microstructures we obtained before. And this is the graded microstructure we obtained in case of the material we focused on. In this case, it is iron, manganese, aluminum, nickel built on a stainless steel. And you see that we have really good properties in terms of microstructures. There is a diffusion zone. We need to get rid of this in the future. So this still hinders a really sharp gradation, but this is what we are working on right now. Okay, so that's all for today. As a summary, the slides I showed before. So we have the ability to print really unique microstructures. We have to think additive, as I said before. So this, of course, is a prerequisite for all the things we want to obtain and establish in the future. And in my eyes, right now, 4D printing is still, of course, a complex topic, but it's the right time to start in the field. And that's all from my side today. So some references for the things I showed in my talk, acknowledgements, of course, to my group here in Kassel and all collaborators. Thanks to you for joining this. And of course, now my question, are there any questions? So thanks a lot.
Thank you very much.